Per National Electrical Code Section 90.24, the maximum allowable inrush current is 18 times the full load current. A 30 amp circuit allows for a maximum inrush of 540 amps. Therefore, based on an inrush current calculation, it appears a 30 amp breaker could trip under those inrush circumstances. Inrush current is a very short-term surge that occurs immediately upon startup. It is not a continuous load. The wire size must support the full load, not the inrush current itself. It is generally permitted to undersize the wire for inrush current, however the wire must meet the requirements for the continuous load it will be subjected to. As far as sizing the control power, it will depend on the total draw of all the connected devices. If the total current draw of the connected devices exceeds 30 amps, then additional circuits are required. Several factors must be considered to determine the appropriate wire size for a given application. Firstly, the ampacity of the conductor must be sufficient to carry the calculated load current. Secondly, voltage drop must be within acceptable limits to ensure proper equipment operation. Thirdly, the conductor must be protected against overcurrent by a suitable fuse or circuit breaker. The National Electrical Code, or NIC, provides tables and guidelines for determining the appropriate wire size based on these factors. These tables take into account the conductor material, insulation type, ambient temperature, and the number of conductors in a raceway or cable. To determine the ampacity of a conductor, refer to NEC Table 310.15b16, which lists the allowable ampacities of insulated conductors rated up to 600 volts, not more than 3 conductors in a raceway or cable or earth, based on ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. For example, a 12 American wire gauge, or AUG, copper conductor with THHN insulation has an ampacity of 30 amps under these conditions. However, the ampacity must be adjusted for ambient temperatures higher than 30 degrees Celsius or for more than 3 conductors in a raceway or cable. Adjustment factors are provided in NEC Table 310.15b2 and correction factors are provided in NEC Table 310.15b3. Voltage drop is another important factor to consider when selecting wire size. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop should not exceed 3% for feeders and 5% for branch circuits. To calculate voltage drop, use the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is the direct current constant, which is 12.9 ohm circular mils per foot for copper and 21.2 ohm circular mils per foot for aluminum. I is the current in amps, D is the one-way distance of feet, and Cm is the circular mils area of the conductor. After calculating the voltage drop, compare it to the allowable voltage drop to determine if the selected wire size is adequate. If the voltage drop is too high, increase the wire size until the voltage drop is within acceptable limit. Overcurrent protection is required to protect conductors from overloads and short circuits. The NEC specifies the maximum overcurrent protection for different conductor sizes in NEC Table 240.4b. For example, a 14 AWG copper conductor is typically protected by a 15 amp circuit breaker. A 12 AWG copper conductor is typically protected by a 20 amp circuit breaker, and a 10 AWG copper conductor is typically protected by a 30 amp circuit breaker. However, there are exceptions to these rules, such as for motor circuits and certain types of equipment. In addition to the NEC, local codes and regulations may also apply to wire sizing. It is important to consult with a qualified electrical engineer or electrician to ensure that the wire size is appropriate for the specific application and complies with all applicable codes and regulations. Furthermore, other considerations can play a role in the selection of wire sizes. For example, in some cases, using a larger wire size than required by the NEC can improve energy efficiency by reducing voltage drop and power losses. This is particularly important for long circuit runs or circuits that carry high currents. In addition, the type of load being served can also influence wire size selection. For example, circuits serving sensitive electronic equipment may require larger wire sizes to minimize voltage fluctuations and ensure proper equipment operation. Also, the environment in which the wiring is installed could affect wire size selection. For example, in corrosive environments, conductors with corrosion-resistant insulation may be required. In high-temperature environments, conductors with high-temperature insulation may be required. When determining control power requirements, several factors need to be considered. Firstly, determine the total current draw of all connected devices. This includes control relays, timers, solenoids, and other devices that are powered by the control circuit. The current draw of each device can be found on its nameplate or in its technical specifications. Secondly, determine the voltage of the control circuit. Control circuits typically operate at 120 volts alternating current or 24 volts direct current, but other voltages may also be used. Thirdly, calculate the total power required by the control circuit using the following formula: power equals voltage times current. This will give you the total power in watts required by the control circuit. Fourthly, select a control power transformer or power supply that is capable of providing the required power. The transformer or power supply should have a power rating that is at least 25% greater than the calculated power requirement to allow for future expansion and to prevent overloading. Fifthly, size the overcurrent protection for the control circuit. The overcurrent protection should be sized according to the NEC and should protect the control circuit wiring and equipment from overloads and short circuits. In addition, it is important to consider the inrush current of control devices when sizing the control power transformer or power supply. Control devices, such as relays and solenoids, typically have a high inrush current when they are first energized. This inrush current can be several times higher than the steady-state current draw of the device. The control power transformer or power supply must be capable of supplying this inrush current without experiencing a significant voltage drop. To calculate the inrush current, refer to the device's technical specifications. The inrush current is typically specified as a peak value or as a multiple of the steady-state current draw. When selecting a control power transformer or power supply, make sure that it is capable of supplying the peak inrush current without exceeding its voltage regulation limits. Also, it is important to consider the ambient temperature in which the control power transformer or power supply will be installed. High ambient temperatures can reduce the capacity of the transformer or power supply, so it may be necessary to select a larger unit if it will be installed in a hot environment. Furthermore, it is important to consider the wiring methods used for the control circuit. The wiring should be installed in accordance with the NEC and should be properly sized to carry the calculated load current. Also, the wiring should be protected from physical damage and should be installed in a neat and workmanlike manner. When designing a lighting control system, it is important to consider the total load in the control circuit. The control circuit should be sized to accommodate the total current draw of all connected devices, including lighting contactors, relays, timers, and photocells. If the total current draw exceeds the capacity of the control circuit, then additional control circuits will be required. Also, it is important to consider the voltage drop in the control circuit. Excessive voltage drop can cause lighting contactors and relays to malfunction or operate inefficiently. The control circuit wiring should be sized to minimize voltage drop and ensure proper equipment operation. In addition, it is important to consider the type of lighting being controlled. Different types of lighting have different current draw characteristics. For example, incandescent lighting has a high inrush current when it is first energized, while LED lighting has a lower inrush current. The control circuit should be sized to accommodate the inrush current of the lighting being controlled. Also, it is important to consider the control strategy being used. Different control strategies have different power requirements. For example, a simple on-off control strategy has lower power requirements than a dimming control strategy. The control circuit should be sized to accommodate the power requirements of the control strategy being used. When designing a lighting control system, it is important to consult with the qualified electrical engineer or electrician to ensure that the system is designed and installed in accordance with all applicable codes and regulations. The NEC provides detailed requirements for lighting control systems, including requirements for control power, wiring methods, and overcurrent protection. It is important to follow these requirements to ensure that the lighting control system is safe and reliable. Furthermore, consider the specific requirements of the lighting control system. For example, if the system includes emergency lighting, then the control circuit must be designed to ensure that the emergency lighting will operate properly in the event of a power outage. If the system includes dimming control, then the control circuit must be designed to provide smooth and flicker-free dimming. Also, if the system includes wireless control, then the control circuit must be designed to provide reliable wireless communication. Remember that safety is paramount when working with electrical systems. Always de-energize circuits before working on them and follow proper lockout-tagout procedures. Use appropriate personal protective equipment, or PPE, such as safety glasses, gloves, and insulated tools. If you are not qualified to work on electrical systems, then hire a qualified electrical contractor to perform the work. Electricity can be dangerous, and it is important to take all necessary precautions to prevent accidents and injuries. By understanding the principles of inrush current, wire sizing, and control power, and by following the requirements of the NEC and other applicable codes and regulations, you can ensure that electrical systems are safe, reliable, and efficient. This knowledge is essential for anyone working with electrical systems, whether they are electricians, engineers, or homeowners. When it comes to sizing conductors for specific applications, several sections of the NEC provide guidance. NEC Section 310.15 details the allowable ampacities of conductors under various conditions. This section includes tables that list the ampacities of different conductor sizes based on their insulation type, ambient temperature, and the number of conductors in a raceway. NEC Section 240.4d addresses the protection of conductors against overcurrent. This section specifies the maximum overcurrent protection allowed for different conductor sizes. It is important to note that the overcurrent protection device, such as a circuit breaker or fuse, must be sized to protect the conductor from overheating due to an overload or short circuit. NEC Section 310.16 is one of the most commonly used tables for determining the ampacity of conductors. This table lists the allowable ampacities of insulated conductors rated up to 600 volts, not more than 3 conductors in a raceway or cable or earth, based on an ambient temperature of 30 degrees Celsius. For example, a 14 American wire gauge or copper conductor with THHN insulation has an ampacity of 15 amps under these conditions. NEC Section 310.15b2 provides adjustment factors for ambient temperatures other than 30 degrees Celsius. If the ambient temperature is higher than 30 degrees Celsius, the ampacity of the conductor must be reduced by the appropriate adjustment factor. This is because high temperatures increase the resistance of the conductor, which reduces its ability to carry current safely. NEC Section 310.15b3 provides correction factors for more than 3 conductors in a raceway or cable. If there are more than 3 conductors in a raceway or cable, the ampacity of the conductors must be reduced by the appropriate correction factor. This is because the heat generated by the conductors can build up in the raceway or cable, which reduces their ability to carry current safely. NEC Section 210.19 specifies the minimum size of branch circuit conductors. This section requires that branch circuit conductors be sized to carry the calculated load current plus an additional 25% for continuous loads. A continuous load is defined as a load that operates for 3 hours or more at a time. NEC Section 215.2 specifies the minimum size of feeder conductors. This section requires that feeder conductors be sized to carry the calculated load current plus an additional 25% for continuous loads. The calculated load current is determined by adding up the loads on all of the branch circuits served by the feeder. When selecting conductors, it is important to consider the type of insulation. Different types of insulation have different temperature ratings and different resistance to moisture, chemicals, and abrasion. Common types of insulation include THHN, THWN, XHHW in use. THHN insulation is a thermoplastic high heat resistant nylon insulation that is commonly used for general purpose wiring. THWN insulation is a thermoplastic heat and water resistant nylon insulation that is commonly used in wet locations. XHHW insulation is a cross-linked polyethylene high heat and water resistant insulation that is commonly used for underground wiring. Use insulation is an underground service entrance cable insulation that is commonly used for direct burial applications. In addition to the NEC, local codes and regulations may also apply to conductor sizing. It is important to consult with a qualified electrical engineer or electrician to ensure that the conductor size is appropriate for the specific application and complies with all applicable codes and regulations. Furthermore, it is important to consider the future needs of the electrical system when sizing conductors. If there is a possibility that the load on the circuit will increase in the future, it is advisable to install larger conductors to accommodate the increased load. This can save time and money in the long run by avoiding the need to replace the conductors later on. Also, it is important to consider the voltage drop in the circuit when sizing conductors. Voltage drop is the reduction in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop should not exceed 3% for feeders and 5% for branch circuits. To calculate voltage drop, use the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is the direct current constant, which is 12.9 ohms circular mils per foot for copper and 21.2 ohms circular mils per foot for aluminum. I is the current in amps, D is the one-way distance in feet, and Cm is the circular mils area of the conductor. After calculating the voltage drop, compare it to the allowable voltage drop to determine if the selected conductor size is adequate. If the voltage drop is too high, increase the conductor size until the voltage drop is within acceptable limits. When working with electrical systems, safety should always be the top priority. Always de-energize circuits before working on them and follow proper lockout-tagout procedures. Use appropriate personal protective equipment, or PPE, such as safety glasses, gloves, and insulated tools. If you are not qualified to work on electrical systems, then hire a qualified electrical contractor to perform the work. Electricity can be dangerous, and it is important to take all necessary precautions to prevent accidents and injuries. By following these guidelines, you can ensure that conductors are sized correctly and that electrical systems are safe, reliable, and efficient.